So this video is going to go through how to use average rate of change. I suggest that you have your Desmos Scientific Calculator app ready to go. So what we are doing is we're going to compare some average rates of change here. Ultimately, since an exponential function is going to change faster and faster, and that average rate of change will eventually exceed the average rate of change of a linear function, we can expect that at some point the exponential is going to outgrow that linear function. We can also compare exponential functions directly based on their average rates of change over the same interval. So the first one we're going to look at here has a table and a graph, and we want to look at the average rate of change from day 10 to day 20 on both of these here and then compare them. So here is day 10 to day 20 on the website A. So 2150 and 1400. These have a difference of 750. And then these have a difference of 10. So for website A, over that interval of 10 to 20, that average rate of change was 750 divided by 10, which is 75. And then here, I'm going to do this in my highlighter again. These are pretty close to being on tick marks, so we're just going to assume they're on tick marks and kind of go with it. So this change here, that's still a sideways change of 10. And my vertical change, I'm going from, these are 300, 600, 900, 1200. So these are increasing by 300. So then this would be 900 to 1800. So that would be a difference of 900. Because I'm looking at this change here. So then over the interval from 10 to 20 here, that would be 900 over 10, which is going to simplify to 90. So by using that average rate of change between that jump from 10 to 20, what they'd like for us to do is predict who's going to have more after 50 days. Well, based on this jump of 10 days, I'm going to assume or take an educated guess that it would be website B, because it has a much larger rate of change initially, with that between 10 and 20 days. So I can make an educated guess that this is my exponential function. And if I look at the pattern here, this is probably going to end up being a linear function. And I know that since this average rate of change at the beginning between days 10 and 20 is much larger, that rate of change is going to continue to be larger than website A. So I'm going to predict that website B will have more members after 50 days. The next one we're going to look at is a table. It's documented the amount of bacteria present in a culture after a certain number of hours. And our goal is to compare the interval from 1 to 3. So here's 1 to 3. And then I'm also going to compare 3 to 5. And then we're going to look at what this means for the function itself. So here, that would be a difference of 6. That would be a difference of 2. So on my interval 1 to 3, this has a difference of 6 over 2, which means my average rate of change for that interval would be 3. Oops. 8 and 31 have a difference of 23. 3 and 5 still have a difference of 2. So my 3 to 5 interval is going to be 23 over 2. Which is going to simplify to 11.5. So what does this mean for the function representing the bacteria population? Well, since these average rates of change are very drastically different, we would assume or make our educated guess that our type of function is most likely going to be exponential. Because this average rate of change has greatly increased, if I graphed it, I would feel pretty confident that my graph would mimic that exponential growth. So here I would say that this would be an exponential function. Based on the increasing average rate of change over those two intervals. And last but not least, I have information about town A and then a graph for town B. It says the population was 3,000 and it increased by 20% every decade. So X represents the number of decades. A decade is 10 years. So town A is going to have an exponential function. I'm going to call them A of X since they're town A. So they're starting with 3,000 people, and they're going to increase by 20% every decade, and X represents the number of decades. I'm going to zoom out a little bit here. So they have said they want us to find 1990 and 2010. Well, from 1970 to 1990 is 20 years. So 1990 would represent 2 decades. So for that, my X value would be 2. (2010), if I did 2010 minus 1970, that would give me 40 years, which would mean that was 4 decades. So X would equal 4. So I need to find for town A and town B my output values or my population values for 2 and 4. And then I'm going to do the same thing down here. Actually, I'll do it next to it so we have some space. So for town A, I'm going to substitute into my exponent the values of 2 and 4. So I'm going to grab my calculator. So I'm going to do 3,000 times 1.2 to the power of 2. So that would be 4,320. I'm going to change that exponent to 4. Now remember, this is people, so I'm not going to have a decimal. So I'm going to do 6,220 so that I don't have a decimal. So now I need to find my rate of change, my average rate of change for town A. So this is a difference of 1,900. So I'll have 1,900 over 2. And that's going to give me 950 for town A. For town B, I'm going to get my data from the graph. So at 2, I'm about right in between there. And at 4, looks like it's right there. So the first thing I need to do is figure out how these are growing. So this is 4250. This is 4750. So here's what I would do. I would do 4,750, and I'm going to subtract 4,250. And then I'm noticing that that takes 2 jumps. This is a distance of 500, so that tells me this one jump here is 250. Okay, so here, if I'm at 4,750, I need to add 250 to it. That tells me this is 5,000, this line here. Now I'm halfway in between that, but 250 isn't evenly divisible. Oh, this is in half. Just kidding. It can be divided in half. Thought I was somewhere else. Lord help us. So now I'm going to add 125. So this y value here, because it's halfway between 5,000 and 5,250, is going to be 5,125. So now I'm going to add 250 here, another 250 there. So 5,750 plus 2 250s, or 500, tells me that this is 6,250. I didn't really leave myself enough room there for town B. So this is 2. So the jump here in between the y's is, I'm just going to write it down here, 1125. So for town B, we got 1125 divided by 2. And again, I can't have, oh, my document camera froze. Can't have a decimal, so this is going to be 562-ish. So the average rate of change for town A are 950, and for town B, it's 562. So based on that jump, town A has a larger average rate of change for that initial interval that we were looking at. I also noticed that town A represents an exponential function and town B represents a linear function. So in 10 more years or another decade, I can assume that town A is going to have the greater population because it has a larger average rate of change between the previous interval that we looked at.